Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams at Michigan State University. Before introducing our distinguished speaker today, I would like to remember and honor the victims of the senseless tragedy that happened on the Michigan State campus last week on Monday. We lost three wonderful students, Ariel Anderson, Alexandria Werner, and Brian Frazier, and several others are recovering from injuries. Our thoughts, prayers, and resolve go to supporting the families and the Michigan State community. Today's public talk is part of an initiative at the Facility for Rare Isotope Beams called the Advanced Studies Gateway. The primary goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today, we have the pleasure of presenting a public lecture by Professor Deirdre Shoemaker entitled Black Holes and Gravitational Waves, Our Astounding Universe.
Both. I'm okay with either.
Professor Shoemaker is a physics professor and the director of Center for Gravitational Physics at the University of Texas at Austin, and a member of the Weinberg Institute. She received her PhD in physics from the University of Texas at Austin. She was a postdoctoral fellow at Penn State and Cornell University before joining the faculty at Penn State in 2004. She moved to the School of Physics at the Georgia Institute of Technology in 2008, and to the Department of Physics at the University of Texas at Austin in 2020. Her research interests center on black holes and gravitational waves, understanding these and other aspects of strong gravity and how they are manifested in the universe. Professor Shoemaker is a member of the Laser Interferometer Gravitational Wave Observatory, or LIGO, scientific collaboration, the Cosmic Explorer Consortium, and the Laser Interferometer Space Antenna, or LISA, Consortium. She is a fellow of the American Physical Society. If you have any questions during this talk, please type them into the chat or question and answer dialog box. At this time, it is my great pleasure to introduce Professor Shoemaker.
Thank you, Dean, very much, and all of you out there. So I'll try to distract us a little bit from some of the challenges in our world. We'll talk about things that maybe won't solve things, but they're fascinating what we can learn about our universe. And a lot of, in the last few years, it's become just a cornucopia of knowledge that we've been able to garner from things that you might think are science fiction. Black holes are popular in movies and in books and comic books, but they're actually a real important engine of our universe. And they give us an opportunity to really understand sort of Einstein's theory of gravity in its most astonishing expression. So that's what I'm going to chat about. So I know you guys hear, those of you who attend these lectures frequently, about all the exciting things, like the lab at Michigan State that Professor Lee is going to be involved in is much different than my lab. My lab is the universe. We cannot make black holes in our building. It would be really frowned upon if we had the capability. So we have to get serendipitous detections. We really have big detectors that sit on right now the surface of the Earth. They just look out, and we wait for something exciting to happen in the universe. And the good news is there often is. I don't know how many of you have been seeing all these James Webb Space Telescope pictures. This is, I think, one of them. It could be Hubble. I might not have updated it. I can't remember. But how astonishing it is if you look in this really dark patch of the sky, and yet it is full of beautiful galaxies and every type. And in the middle of each of these galaxies, there very well could be a really large black hole. And so this is our playground. And the better our instruments get, the more information we can glean from all this that's happening in our universe. So yeah, this was the Hubble Deep Field I should have replaced it with the James Webb, but these telescopes are amazing because they're really looking back in time, since it takes light travels to us at a finite speed. So when we get this light, sometimes you'll hear us talking about things happening 100 million years ago because it took that long for the light to reach us. So in a sense, astronomy often acts like a time machine. So this is a center of a galaxy. If we start beaming down into one of these galaxies far away, we might see things exploding. There's a lot of violence out in the universe too. You know, the way that our planet came to be and the way all the stars formed, a lot of things are happening as the universe interacts. And so this is an image of, this was M87. I couldn't remember for a second. This is M87 if we look at it with light. This is M87. M87 is a bad name for another galaxy. I don't know how they pick these names. M87 is not the most exciting name I've ever heard of. But this is an image of the black hole at the center of that galaxy. And so what happens is that we can't see black holes because they don't shine light. But if there are things in the vicinity of a black hole, like stars, gas, then as they fall into the black hole stretches, is such a strong gravitational pull, it actually causes the light of matter as it falls into the black hole to emit strongly. And so this was the first image from the Event Horizon Telescope that showed us that we can actually see that the black inside of this, this is like the last light falling into the black hole, and we can actually image the size of that black hole, which looks tiny here, but is really quite large, larger than our solar system, if we could actually measure that region inside the donut there. And so what we found is that you see these Event Horizon Telescope images that's actually being able to capture this with radio waves. So there's so many ways we gather this information that's out there in the universe waiting for us to measure it. And this radio telescope, which I'm not involved in, but I find it another beautiful way of learning about strong gravity and black holes. So this uses radio dishes, just like you might, pick up radio on a radio station, but it's all over the world. And so they can use telescopes all over the world and recombine the data so that the telescope acts like something that's much bigger than any of the individual parts. So this is how they took that beautiful image of a galaxy called M87. So they're using radio waves, and then they recreate this image that we see before us. There's another way to do this. So the first way we knew that there was a black hole in the center of our own galaxy was from measuring with another telescope called Keck out at UCLA. Each one of these colorful blobs is an individual star, just like our sun, that's orbiting something dark in the middle that you can't see. So you see all these traced patterns are the orbits of stars going around something that isn't shining. And again, this, 0.24 arc minutes probably doesn't tell you much, but what it's telling you is this region, again, is about the size of our solar system, a little bigger. I mean, the size of the black hole in the middle is about the size of the solar system. So you can see that they looked at this long enough that they could actually use some pretty basic physics, like you might learn in high school physics or first year physics in college. You could use Kepler's laws to figure out what the mass of the object these things have to be orbiting around is. And it's about 4 million times the mass of our own sun. So something really big lurks in the middle of the galaxy. Ours is called Sagittarius. In that region, we call it Sagittarius A star, but you can't see it. And so then you start to be able to constrain what could possibly be causing the orbits to turn like that, to be attracted to something that you can't see. And one of the very few objects that it can be is a black hole. So you might ask, how do these things happen? How do these black holes come to be? And there's different mechanisms, and we don't really know all of the different ways black holes form yet. But one of the common ways is that you have a really massive star, much bigger than our own sun. Our sun's not going to undergo this. If you have a really massive star, eventually it runs out of fuel and it starts collapsing in on itself. And typically these things undergo something called a supernova explosion, where they push out all the star, a big envelope gets excited, gets pushed out into the universe. It's actually a lot of where our elements come from. So the joke is that you and I are made of supernova dust, and that's very true, that's where we make these elements. But if we look at what's left inside when the supernova explosion's over, it could be nothing. It could be that everything disappeared. It could be something called a neutron star, which is sort of the most compact object that isn't a black hole, or it could be a black hole. And so these are things that form black holes that are like a bit bigger than our sun, but not the size of those ones in the middle of the galaxies that I was just talking about. So the fate of large stars can often lead to one of these super compact objects called a black hole. And it's called a black hole because nothing, not even light, can escape it. So if you imagine if I took the sun and I was all powerful, which I'm not, and I could squeeze the entire mass of the sun into the size of like a golf ball, I would create a black hole. We would not die. We would not get sucked into the black hole here on Earth. Our orbit wouldn't really be changed, but we would not have any light. So we'd be doomed, but we wouldn't be sucked into the black hole. It's not a huge vacuum cleaner. The problem is that if you actually go past its horizon, then you can't escape. Then your future path is always directed towards the center. So it is a fascinating thing that these could be so ubiquitous in the universe when they seem kind of odd and science fiction-y. One of the fascinating things about either neutron stars, well, especially neutron stars, is that black holes are sort of the end of things, right? We can't really get information back out. So things go in and they don't come out. I mean, maybe when we come up with a new quantum theory of gravity, we'll learn some things about how to understand better the interiors of black hole. But classically speaking, it's basically something we can't learn about. But neutron stars are the opposite. Neutron stars, these really compact stars that are just that limit before you'd form a black hole. They're fascinating inside. They have basically all physics in there. It's dense, hot. It's an amazing experimental world, and it could teach us things about our matter here on Earth that you can't probe in other ways because it's it's density and temperature that we can't do in terrestrial labs. So all these little N's and Q's and letters are really labeling all the different particles and quark and everything that's going on inside the center of a neutron star. And I mention this now because I'm going to talk about what we can learn with gravitational wave detections, and this is going to be important for that topic. So this image is back to black holes. Black holes are my favorite because that's what I study. Neutron stars are just really complicated, so I prefer to keep my my life clean and matter-free, so I tend to study black holes. But if you imagine I had a black hole and it was sitting in between us and the center of our galaxy, black holes are such strong gravitating objects that they would distort the light of the Milky Way until it looked like this. So it makes light bend. All massive objects make light bend, but black holes are the most compact massive objects, so they make light blend in these beautiful ways. If you saw Interstellar, it's getting old, that movie now, but if you saw the movie Interstellar, a lot of the effects they showed you were true effects. They actually calculated how would light be responding in that wormhole, in that supermassive black hole, gargantuan, or whatever its name was. Those effects were true expressions of general relativity. They're just kind of wild. So the point, I guess, I want to make as you spend this precious hour of your time with me today is that the universe is vast, and there's really amazing things that happen. And that neutron stars and black holes are the most compact objects that we know of, according to current theory. I like to keep that door open as we learn new things about the universe. Our knowledge always changes, and sometimes we can be surprised about what's possible. And so I want to figure out how can we learn about something in the interior of a neutron star, which is such a crazy dense place. And was Einstein right about the way he predicted, his theory predicts black holes? Those are the types of things I'm interested in learning about. And how do we take these objects that seem so esoteric and use them to learn about the universe? What else does it teach us? And since 2015, so we've been looking at the universe using light since we opened our eyes, right? People have always looked up, told stories about the sky, and then we got more and more sophisticated with our ability with telescopes to gather in light. But in 2015, we began to look at the universe with a new way, which is not light, called gravitational waves. And I'll talk about that a bit too. And so this is the reason why we're gaining significant amounts of new knowledge right now, because we're in this moment when gravitational waves has become possible. And it's only been since 2015, although I've been doing it. So what are gravitational waves? This is a cartoon. It's from PhD Comics. It's a little hard to see the title in gray. PhD Comics is great. It's called Piled Higher and Deeper, but it often takes a little moment of the life of graduate students. So if you have some friends who are graduate students or your own, this is a great comic for them. And what they're doing is they're explaining a little bit about gravitational waves. So light comes from accelerating an electron particle. Gravitational waves come from the non-uniform acceleration of mass. It could even be this cracker or nut, whatever it is. So if this thing were accelerating in a non-uniform way, or even my hand, I can produce gravitational waves, but they'd be really weak. We'd have no chance of detecting them. So that gravitational waves are produced whenever masses accelerate and they distort space and time. So they're literally it's almost like if you bang a table, you leave your hand on the table and you bang the table and you feel the vibrations coming. Gravitational waves are a bit like that, except the table is space-time itself and the banging is the mass. And that vibration we feel, you can use that as an analog of what the gravitational wave is. You feel the table having a bit of an oscillation. So a gravitational wave stretches and squeezes space-time as it propagates out from whatever disturbance caused it. So everything with mass or energy makes gravitational waves. So if these two people started dancing around each other, they would create gravitational waves, but they'd be so small. So what you really need is the most compact massive objects, like our black holes and neutron stars, to make it possible to measure them here on Earth. So gravitational waves were predicted 100 years ago. It took until 2015 to see them for the first time because they are so tiny. We just didn't have the capacity to engineer these detectors that would be sensitive enough to detect them. But now, what is it? Is it already 8 years later? Wow. 8 years later, we went from never seeing gravitational waves to having seen 90 events. So this is a plot from LIGO, which is that gravitational wave detector mentioned in my little bio. And it sits there on the surface of the Earth. And if a gravitational wave hits, the detector moves and we pick up that change in the detector from the gravitational wave passing through. And then we take that information we gathered and we use theoretical predictions that people like me do. I'm a theorist. I solve Einstein's equations for two black holes merging. I tell the detector people, this is what that looks like. And then they use that to actually pick up the information. And then we see all these black holes. So the x-axis is, the horizontal axis doesn't tell us anything, but the y-axis says how massive are these objects. The ones in blue are the black holes. And there's three dots associated with each black hole event. There's two black holes initially, and then about 0.2 seconds later, there's another big black hole because the two black holes have collided. So we're seeing these, they've been orbiting each other for millions upon millions of years, and we're just seeing them in that last second as they merge into each other, as they collide. If you look and wonder what the red is if the black holes that were discovered by electromagnetic means from seeing a star bit disrupted around the black hole. And so we can measure that light similar to the Event Horizon Telescope, but now on a small black hole scale, and inferred what the black hole partner had to be. And the orange are neutron stars. So you see, we don't see as many neutron stars yet, there's a lot more black holes. We've only seen 2 binary neutron star events. And we've also seen black holes and neutron stars collide. And the reason for that is because the neutron stars are less massive. You can see from that mass scale on the vertical axis, these black holes can be big, 100 times the mass of our sun, where the neutron stars tend to be about the same mass of our sun. So they don't give off as much radiation. We can't see them as far away. They are likely to be more frequent, but we can see the black holes so much further away. And that's why we have all those blue dots and fewer orange. So this is what LIGO looks like. The United States has 2 sites. That was kind of quick. It's dangerous for me to go back. Let's see if I can do it. The US has 2 sites. We have one in Washington State and one in Louisiana State. And if I go back in time here for a second, you see that these are 2 vacuum tubes. They're 4-kilometer long concrete tubes with a vacuum inside, and there's laser light being shined down these tubes, and there's a mirror hanging way 4 kilometers away, and another mirror hanging 4 kilometers away here, and it's an interferometer. The links are the same, and when a gravitational wave hits, the links change minutely, 10 to the minus 21, but they change. Of course, anything changes in links, right? Tumbleweed, earthquakes, you walk too hard, you're going to change the length of these. So the name of the game here is that you have to be able to isolate an actual detection versus noise from everything else. Having 2 detectors helps, because the same tumbleweed in Washington is not happening in Louisiana. There's a tree falling or something else. So that helps us isolate. It's a very sophisticated problem, isolating all the noise sources and coming up with a true event. So now we're going to peel open these concrete tubes and peek and see what's happening inside. So we'll go in, and now this is a cartoon of the laser. This beam split, and it goes down the 2 arms and shines, bounces off the mirrors. And that little square is our detector, and it's measuring the how the phase shift of that light comes in. So it's using the light's phase and frequency. And we get a measurement that if the arms are the same length, nothing happens. We see no light. And if the arms are changing length, then we come up with a light pattern at the detector that you're seeing right now. And we're measuring the frequency and the amplitude of that light. And that actually gives us the information about what caused the gravitational wave event. So from this pattern, all this beautiful black hole picture I just showed you, that's where it comes from. But how tiny is this measurement? That's an atom. Now we're going inside the atom. We're still going in. It's really small. Yeah, I think we're there. So we're looking for something this tiny in the inside of an atom. We're looking at a change in length that's on the order of 10 to the minus 21, which is the length, the change in length over the length. I mean, that's small. It's like smaller than an atom. So this is what made this such challenging. I'm glad I'm not an experimentalist, is I think my takeaway there. So I mentioned the 2 LIGO experiments. This is a National Science Foundation project, and there are others. This is a worldwide collaboration. So there's a detector in Italy, and there's a detector in a small detector in Germany. There's one in Japan, and one coming online in India. And this was the first discovery. Looks so anticlimactic when I put this up. It's funny. So science can be a long slog. So I was a graduate student in the 90s, and I studied 2 black holes colliding at a time when we didn't know if the universe actually came up with 2 black holes in orbit around each other, because we couldn't see them, couldn't see their light. Therefore, we were blind to them. So we didn't know if they were there or how many. But nonetheless, I spent a long time solving Einstein's equations using supercomputers for these 2 black holes. Why? So we could predict this little red line that looks like a messy sine wave, right? So actually, you see the NR in the second figure in red. That was from numeric relativity. That's what I do. And so that was our prediction in the second row there. The first row is what the detector saw. Now, on 2015, when this event came in, I couldn't believe it, because I could look at that and say, that looks like 2 black holes colliding. And this was the detector had just turned on. It had gone through its commissioning phase, and we were shocked by the quality of this signal. In fact, we didn't believe it was true for a while. We thought somebody in the higher ups were messing with us, were testing the system. But nonetheless, it was a detection, an event. And the bottom more colorful row is showing you what it looks like in time and frequency. So it's this like little chirp up of signal. And the middle ones are showing you what the signal looks like if you plotted it versus time. So this wave signal is how that light is coming in and changing the lengths of those arms. And that's what you pick up in your detector. And you can see from the strain, which is just the change in length over length, that it's that tiny number that I mentioned before. I kind of have the Q&A open, but I'm not going to answer it because I realize that will be too distracting. So I'll try not to watch too hard. So that first binary black hole, so the first gravitational wave detection and the first time we saw two black holes. So both of those first happened with this event. And so you have these two black holes orbiting each other. They merge and we call it ring down when they're like a bell, because once a single black hole is there, they don't give off any more gravitational radiation. It goes quiet. So that's why the signal chirps up and then goes quiet here on the right in the red that you're looking in the middle. And that lower plot, I think, is kind of fun because it shows you how fast these black holes are kind of moving when they fly. We're doing like 60% of speed of light. So these things are the size of, I don't know, pretty big city, moving at 60% of speed of light. So we wouldn't want to be in the middle of it. It's weak by the time it reaches Earth, but it's certainly not weak when you're in the vicinity of the black holes. On the right, I show you a completely useless thing. I show you what the Einstein's equations look like in fancy math talk, and you wouldn't believe how hard it is to solve that equation. And actually, so we use these supercomputers, which is the picture below, but it took us, I think the first idea of being able to solve Einstein's equations came about in like 1950, and the first solution happened of the two black holes with gravitational radiation, like one we would actually see in the universe, happened in 2006. So it took a long time to be able to get the computing and the math good enough to actually do this. So this is what it looks like. These are two black holes. Now you saw them zoom away from us. As they orbit each other, that gravitational wave in white is increasing. And then once they collide, it just decays away. And then the Earth is somewhere in that picture. So I'll play it one more time. Oh, it's so fast, I can't even catch it there. So here are the two black holes. You see, boy, that thing doesn't want to slow down, does it? You can see that they have arrows associated with them. So they each have a mass. They each have they're spinning about their axis in some way. And that black line is just tracing out their orbit. And then this white down here is the gravitational radiation that we're observing. This is the theoretical prediction. These things have been orbiting for a long time, but I can't do it forever on my computer, right? I have a finite amount of time. So I have to start them off at some closer separation. And then we see how it goes. So then they're orbiting, they're getting closer and closer. They're losing energy because they're giving off gravitational radiation. And so that's why they get closer and closer. And if you zoom in, it's really hard to do it. Oh, it's too late. The background's a little dark, but if I go back, you might see it. Do you see this black hole? That's the merged black hole in the middle. And this contour of purple and blue is the three-dimensional rendering of the gravitational radiation. And then for LIGO, we just do this line of sight where you get this white line. So we give LIGO the white, basically it looks like a sine curve. All this work for something that looks like a sine curve. So that's what we do. So that was our binary black hole. Then a little while later, the first detection of neutron stars happened. And colliding neutron stars allows for a lot more things we can do. So black holes help us test Einstein's theory, but neutron stars allow us to test a lot because you can actually see neutron stars with light and gravitational waves. So this event that happened was the first time we saw gravitational waves from two neutron stars colliding, but we also saw, not me, but telescopes also around the world also saw the electromagnetic light. And they could constrain the speed of the gravitational wave to a part in 10 to the 15. And one of the most exciting things this discovery brought us was that where do elements come from? I made the joke earlier that we're supernova. Well, we also could be binary neutron star collision remnants. So the universe starts with simple things in red, like helium and hydrogen, and this elements chart to the right. And then inside stars, we get the ones in blue. So we get silicon and oxygen and all these other sodium, all these other elements form there. But then when what we did not know before this event is all those yellow ones can happen not just from supernova, but also be produced in neutron stars. So we saw just an amazing amount of creation of elements happening because of this dense, hot soup when the two neutron stars collide. So there's some really good talks about how gold and platinum and all our precious metals are coming from two neutron stars colliding. So this is my world again. This is what it looks like when we simulate these on the computer. On the left is the matter, and on the right is the production of gravitational waves as these two neutron stars come towards each other. But if you notice for a second, you can start to see these stars get distorted and elongated because they're not black holes. They're extremely dense matter, but they start to get ripped apart. And this is why you can see so much amazing production of elements happening, because there's a tremendous amount of stress happening to the matter inside those neutron stars. So we still see our gravitational wave pattern on the right, and the neutron stars are now pulling each other apart, and they're going to form a single star for a second, and then it will form into a black hole at the end. And this is the gravitational radiation we see. So this is what it looks like when we predict it from the viewpoint of Einstein's equation. Okay, I feel like I've babbled a while. I'm a fast talker, and I know that's a problem. And I want to leave a lot of time for questions because I can see them all coming in. So it might seem like, well, it feels like to us after getting 90 events that, you know, how much better can this be? But I heard someone make this analogy last week, and I think it's a good one. We've only been at this game for what, 7 years? So it's like we built our first telescope like Galileo did, and we pointed it to the stars and we saw all these amazing things. I can't imagine what it would have been like the first time to see planet, you know, Saturn or whatever, right? So we're babies. And the ground-based detector, the picture I showed you of LIGO, they're going to keep improving. So right now we're not taking any data because the detectors are being improved. They're not growing the arms right now. They're just changing some of the aspects of the detector itself. And so when that comes back online again, which is expected to be in May, we expect to now see, we saw 1 event, 2 events the first year, then we saw 10 events the next time we ran it, and then we saw like 50 more. So it's exponentially growing because it keeps getting more sensitive. And then we can see further and further away, so more events are taking place in that volume. So when LIGO turns back on, we're expecting to see hundreds of events to the point where it's going to start to get hard. You know, right now we get 1 at a time, but that will change at some point. We'll start to get multiple events. Meanwhile, I'm also part of the LISA mission, which is to put LIGO in space, basically, kind of. So this is an ESA-led mission with NASA partnership. And the idea is in this picture here. So I mentioned really briefly that part of the problem on the ground is everything jiggles the Earth. And you jiggle the Earth, you change those arm lengths, and you cause a lot of noise that makes it harder to pick out the signal of the actual gravitational wave causing the arm lengths to change. So if you imagine if you can put that in space, it'd be better because space is quieter. The problem is, of course, that we can't put big tubes in space. So what we're going to do is fly 3 satellites in the triangle pattern, as you see here. And the bright light you see are actually lasers. So each satellite will have 2 lasers that will be pointed at the other satellites. And then the satellites will have a telescope to measure that light coming in. And I don't know if you can see my camera, but the masses are freely floating. The thing that's going to actually feel the change of gravitational wave is a square this big. It's tiny. It's made of tungsten, so it's very heavy, and it's freely floating at the center of each of those satellites. And we're measuring the movement of that due to gravitational radiation. So in LIGO, we're measuring the movement of a big mirror. It's actually pretty big. And it's suspended because we can't drop it. It will fall to the ground. So we're only sensitive to 2 degrees because we have to hold the mirror up in a pendulum pattern. In space, we'll actually be able to freely fall that mass, And the satellites just have to make sure they don't touch the mast. They'll carefully move around it. There's actually been a proof of principle of this called Pathfinder. So we know we can successfully do that. We've never done 3 satellites, and those satellites are 2.5 million kilometers apart. So that triangle you're seeing is huge. It's 2.5 million kilometers for each arm. And the system, the triangular system, would be orbiting the sun, trailing behind the Earth, as you kind of see from this picture. So it will be sensitive to so many things. And the arms are so much larger than LIGO that it increases, it can see the merger of really massive black holes like those at the center of the galaxy, because it depends on the length of the arm, what we're sensitive to. So this is going to launch in about 2034, 2035. We're just about to hit the phase where the parts are going to be built. It's a very busy time in the LISA world right now. It seems far away, 2035, but 10 years actually isn't very far away. So everything is moving pretty rapidly now. So I didn't put all the pictures, but I also want to point out, not only is this happening, but we're also going to at some point upgrade the ground-based detectors and make their arms longer. The Cosmic Explorer is maybe what will happen in the United States, and it would take those vacuum tubes I showed you in LIGO and make them like 40 kilometers long and make them much more sensitive. Europe has its own plan called the Einstein Telescope, but a similar design. So this is really a partnership, the gravitational wave detection. All the LIGO detectors, Virgo, all the ones around the world, we work together to do this science. So it is a really large collaborative approach. It's not individual detectors working against each other. We do better science when they all come together, because it allows us to point on the sky and take better detections. So it's very much collaborative effort. So here's another of my images. We do them a lot because this is what we spend our lives producing, these gravitational waves from black holes colliding. So I just wanted to give you a sense. This particular image I'm showing you happens to come from a detection that happened in 2019. It was the most massive black hole binary we saw to date. And so we really, I made that comment that we had just started pointing a telescope, but already we're basically going to jump in just a few years from getting our first detections to seeing almost the entire universe. By the time the ground-based detectors are improved to Cosmic Explorer, by the time we go to space, we should be able to see every black hole binary out there that's merge. We'll see the entire universe of it. So we'll jump in 2 decades, what took hundreds of years to do in light. So it's going to be pretty amazing story as we go on the next few years. And we never know what surprises might be ahead of us. Just because right now Einstein's equation successfully predicts everything that we've seen. Everything's been consistent, but it's in its infancy. So we certainly don't take for granted that we might not find a smoking gun of an alternate theory telling us something new about the universe from this. And I know this talk series has had cosmologists and others speak to you, and you might have gotten the hint that we're all looking for. We don't know as much about the universe as you might hope. We don't really know what 95% of it is. So this is another way we're trying to get at that truth. We're looking for flaws in Einstein's theory of gravity so that it could give us a clue on which way to develop it next. So almost everything will be, everything's behaving as we expected it to, but as we get more and more sensitive, we open up the possibility of seeing some small flaw that will point us in a direction to take theoretically for the years to come. So gravitational waves are unique because they really can see inside these super compact objects that we've never been able to do before. And it's the best time. I mean, I might have started this work when it felt like there was no hope, but I've certainly been rewarded with lots of fun things now. Every year we learn new things, and it's just beginning. So I hope it's going to be a fun ride for decades to come. So thank you.
Thanks so much. That was a wonderful talk about some really exciting physics. Thanks so much.
Look, it's my own phone. Oh, it's terrible. Sorry.
So, yeah, there are some questions in the question and answer. Perhaps you can pick the ones that you think you were able to answer. You know, there's quite a lot, so go ahead and choose the ones.
Yeah, my screen just turned off for a second. Sorry about that. Do you want me to stop sharing?
Sure.
I don't know if that's better or worse. Okay, I can put it back up if someone has a question. Hi, Jordan. Why do quasars shoot plasma? So what's really fun about a lot of this stuff, so quasars, we often are talking about the centers of galaxies having these really big black holes. So what's happening is the black hole actually isn't shooting anything from its interior out in the quasar. It's not, so there's big jets associated with quasars and associated with black holes, but it's the matter falling into the black hole that's actually generating all this light. So if you think about that image I had of the Event Horizon Telescope of that donut, that stuff hasn't fallen into the black hole yet. And that's what we're seeing. So some of the light falls into the black hole lost to us. We don't know about it. But other light is whipping around those black holes, and it creates like huge jets that come out to us. So we're seeing the light that does not fall into the black hole. And that's why we get all this plasma and other fascinating things in the vicinity of a black hole. I do not know how quantum loop gravity works, Anonymous. But if I did, whoop, that's Nobel Prize material right there. So the idea of for those of you who are really interested in the string theory versus quantum gravity, I'm not an expert. I'll just give you a few sentences. So one of the ways to try to figure out, if I talked about light, we have a radiation theory of light and we have a photon, which is a single particle of light. So we can quantize light. We can't do that with gravity. We understand gravitational radiation, but we don't have the quantum limit of it. We don't know what the graviton is. We can name it, but we don't have a theory that would predict a graviton. So this is the famous problem of quantum mechanics and general relativity. They don't get along. So there's two options. You either assume quantum mechanics is right, kind of, I'm not saying this too well, and you go after string theory, so like a new theory of gravity, or you kind of assume that the idea of general relativity is right, the space-time concept, and you try to quantize space-time. So loop quantum gravity is taking that approach, sort of like the geometry approach, space-time approach, and trying to build a new theory from there. Both sides have a hard time predicting anything we could measure. So it's still, we still don't know what the right theory is. They're trying all over the place to make predictions we can measure, but it's hard to do. Meanwhile, we're all looking at things we can measure, hoping to find some direction to take to point us in the right direction. So I hope that helps. Harina asks, some stars are so big when the explosion happens, the black hole and the star coexist. The core is the black hole. They were called black hole stars and existed for Arthur. Okay, so I think what I can imagine is being said here is that if you have a situation where the star starts to collapse, you would form a black hole, and you might still have outer shell of the star exploding. And so in some sense, you have a black hole inside of a star. I can imagine that happens. I didn't know they were called black hole stars, but it's really cool. I'll take a look at those. And I imagine they can. I mean, the black holes will live there for basically forever. So that's interesting. Zulkifli says, on the plot for solar masses, how are the two neutron stars different in masses? So the neutron stars tend to be about 2 solar masses. Black holes, we think, are above that. So 4 or 5 solar masses and higher. This just comes from the mechanism that created the neutron star. If you try to make a neutron star much bigger than 2 solar masses, to the limit we understand matter, it will form a black hole. So that's why there's a limit to the mass of the neutron star. So they're always smaller. So they were those low orange ones because they're limited. They have a mass limit that we don't know precisely because that depends on the details of the matter, but it's something we're very excited about. Because if you can really understand the precise relationship of the size of the neutron star and its mass, you learn something more about matter itself that's exciting for a lot of people. There's a lot of different directions you can take this research and learn things. Another anonymous says, why are these signals so short? Okay, yeah, for such large bodies. So one thing I didn't mention is these LIGO signals are detecting things that are about 50 times the mass of our sun, right? Small black holes. And these things have been orbiting for millions and millions of years, but we're only sensitive. So the closer the black holes get, the higher the amplitude, the stronger the gravitational wave signal. So we're catching them at their peak, which happens when they merge. And when that happens, it's about 0.2 seconds. So we don't see them long in the band of LIGO, but you're seeing them at their strongest moment, which is right when the two black holes merge. So that's why it's so short. Now, if I make these black holes huge, if I collide 2 million solar mass black holes, and I have my LISA detector on, it would see them maybe for up to a year. So it would see those black holes orbit for a lot longer, and then see the merger just like ground-based does. But because it's such a bigger detector, those arm lengths are so large, it changes the frequency they're sensitive to, and you would see the signal for much longer. So it's basically, it's related to the arm length detector, which ones we're sensitive to and how long we can see it. How, you have to be really sensitive to see the earlier orbits because the gravitational radiation isn't as strong. So those things we'll see for longer. The signal itself exists. The signal itself has been building for millions of years. It's just when are our detectors sensitive enough to actually see it is the problem. So I hope that answered that question. Karen asks, I thought the elements like indium were formed in supernova and neutron star collisions, not dying low mass stars. Oof. Yeah, I would agree with you. I don't know how massive those low mass stars are. Sorry, that's an element of astronomy that I kind of ignore. That's a good question, Karen. I apologize. I don't have an answer. Another anonymous, when you say that the neutron stars take a second at the end of the dance to form a black hole, is that actual reality of time or a figure of speech? It's a really good question, a little unknown. So when we solve them on the computer, it takes less than a second once they start to be distorted and then form. But two things can happen as that distortion. They can last longer if they form what's called a hypermassive neutron star. So they're being distorted, and before they collapse into a single black hole, they form this crazy, weird mess. And then it forms into a black hole later. And I don't know the exact time scales there, but that could be several seconds. So there is a time scale associated with that. But we don't actually know what's really inside neutron stars. We don't have what we call their equation of state down. So there's a lot of uncertainty of our knowledge of this stuff because there's no way to predict what's in there because we can't make it in a lab. So we really need the gravitational wave detection to tell us more about what's happening inside those neutron stars as they collide. The problem is neutron stars are so light compared to the black holes that we haven't actually seen their merger. We've only seen the final orbits, and then they merge, but not within the sensitivity band of the detector. So we actually haven't seen that really rich part of the neutron star merger yet. When we do, it's going to be really, really game changer. When we can actually get the detectors to be sensitive enough at that frequency, which is a higher frequency than we have, it will be amazing to see that. So so this is Dina, how exact are the simulations? Are we considering the magnetic interactions or just the mass, viscosity, double, all the stuff? Okay, so I like black holes because I only have to do Einstein's equations right. There's no matter. So when we're doing two black holes, the simulations are correct in that we are not modeling any missing physics. If general relativity is right, we're right to the ability for us to solve the equation. So we take a continuous equation and we discretize it. So, we can't do an infinite resolution, but we can tell you our errors. So the binary black hole simulations are pretty good because we can predict what our errors are as long as Einstein's equations are true. If you talk about neutron stars, it's a completely different ballgame because the neutron stars are now is gravitating almost as badly as the black holes, but now you have everything possible under the hood in there. So you need to know neutrinos, you need to know magnetic fields, you need to know everything. This is not as well done because we don't even know all the physics, what equations of state we should be using. So the binary neutron star stuff, when the gravitational wave representation is pretty solid, because all those details, the messy details of the matter at the neutron stars, doesn't imprint itself very strongly on the gravitational waves. That's mostly the matter, the movement of the masses, except for the for once it merges, because then you get this question of, do you have a delayed merger? Because there's a hypermassive neutron star. There's a lot of messy physics in there. So the gravitational waves, though, are pretty solid. But the mergers and stuff, there's so much physics that's missing in there, and different groups are tackling it from different ways. Some people are putting the neutrinos in, some people are doing the magnetohydrodynamics, but it's not, there's no one code that does it all, that predicts it the best. So this is going to take a while for this full thing to develop. It's definitely a hard problem. So John asks, and you tell me when I'm going too long. John asks, could these instruments detect white holes? So we don't think there are white holes in astronomy. So white holes are the opposite of a black hole, if we're using the same language. So you imagine a white hole with like, nothing could ever fall into it. Everything always falls out. But that while we can do that theoretically using Einstein's equations, we don't see that as a consequence of matter. So we can get a black hole because a star collapses into a black hole, but I don't know how you would form a white hole in the universe. So we don't have any expectation that white holes exist. Could we detect them? I don't know how we'd see the white hole. I don't know what a gravitational wave would look like from a white hole. So that's cool, though. I should think about that. I'll think about that later, but I don't know off the top of my head. Okay, large circular accelerators may be sensitive to gravitational waves. LHC is 8.5. Okay, so the LHC in principle would detect black holes, but I don't, Jenna, maybe you know better than I do, but I don't actually think they would detect gravitational waves from these black holes. They would detect an evaporating itty-bitty black hole. So these two particles, there are some theories that would predict that in these particle accelerators, you might create really, really itty-bitty black holes. And those black holes are so tiny, they could undergo evaporation in the timescale of the experiment, and we would detect the signature of that evaporation. So it's a different thing. I haven't heard them. I don't think that I think the masses are too tiny that you would detect the gravitational waves. Some people talk about using atom interferometers to detect gravitational waves, using how sensitive we can understand the atom, but that's not in the LHC. So I'm not 100% sure of all that, but there's maybe two different things coming together. Then Dean asks, what are the other approaches for studying black holes? So the entropy, so all this stuff that's listed here, there's a lot of work we do to theoretically understand black holes. I just said the evaporation of them from Hawking's radiation. All that stuff is hard to see with what I'm talking about, because we're doing, these are really big black holes that are astrophysical. And they're the ones that we're getting these signals from. Primordial black holes we might use to do this like Hawking radiation and see the evaporation, because they might be evaporating today and you'd see that excess signal. We wouldn't see those with gravitational waves. We might see two primordial black holes merge in a future detector if we can figure out the different families, like when was it, we have to figure out when these black holes got made throughout the universe and what they might be telling us about their origins. So there's hopes that we could get a little bit at primordial black holes, but the entropy conservation of black holes and all that stuff, gravitational wave detectors are probably not going to tell us. They might tell us if an event horizon is really true or if it's something else, like a firewall. So they'll get at some parts of as we march away from general relativity, but not all of it. So there, we'll have to look at something else. Okay. So with electromagnetism, do we see black holes the size of 20 solar masses? No, oddly enough, the X-ray binaries typically have a black hole partner that was smaller, not as heavy. These 200 solar mass black holes, nobody even predicted they existed, like 200 solar mass black holes colliding. maybe it comes from a different epoch of the universe. The X-ray binaries are usually closer to us than the big black hole we're seeing from gravitational waves. And so maybe they were just coming from the universe having different situation and that made bigger stars. So that kind of thing is what people are researching right now. When LISA Einstein telescope comes online and we become more sensitive, will the waves from a lot of different events interfere and reduce? Yes. So the thing I'm spending most of my time on in research right now is the fact that LISA will see a massive black hole, maybe for months to a year, and then underneath it, like popcorn, are all these other events that people want to see happening, and we have to do it all at once. So my team is spending its time right now trying to figure out how accurate do we have to predict the massive black hole binary so that you can remove it and come up with all the other events that are happening without contaminating it. So that's a really big open thing that we're all working on really hard right now. Oh goodness, there's more element questions that I'm going to skip because I'm not an expert in that. When we solve the GR equations, what are we exact about? So what's interesting, so I don't know how many of you guys remember Newtonian physics, but when you solve the two-body problem in Newtonian mechanics, you're solving for the force, right? F equals G, M1, M2 over R squared. Einstein equation is different. So Newtonian mechanics would just have these two bodies on a fixed flat background. GR, we solve for the geometry of the space-time and the dynamics at the same time, which is what makes them so hard. So when I say that we're being exact, we are predicting the motion of the black holes, the geometry of space-time itself, so the fact that it's warped from the fact that these black holes are moving, and the gravitational radiation. So we're solving sort of everything about it. GR that's what makes GR kind of a fascinating theory, because it's not, we don't have a given, we live in a world where our space is kind of given, it's flat, you know, I'm not expecting space time to curve as I walk around, but that's not true. So we have to actually come up with the geometry and the dynamics. Should I do David's and then we're done?
Yeah.
How can we tell if the inner event horizon and the Kerr metric is actually physical or a mathematical artifact? So what we're trying to do there is we have a prediction of what Einstein tells us should be true using something called quasi-normal modes really well. So we look for deviations of that, because a lot of theories that predict something else other than an event horizon slightly change the end signal. So as we get more sensitive, we're looking for deviations in that end signal that would then say, all right, GR is not right. Can we now actually figure out what could be causing deviations? It's a hard game to play, but you should see as we get more sensitive, constraints happening more and more. Okay.
All right. Well, thank you, Professor Shoemaker, for a wonderful talk and answering so many questions in such detail.
No problem. I try. I don't know.
So thank you, everybody, for coming. Our next talk will be next month. But until then, I'll take care. I'll see you then.
Thanks, Ian. Thanks for the invite.